Welcome to our latest video, which gives an introduction to redox titrations. This video is suitable for A-level students. By the end of this video lesson, you should be able to write ion electron half equations for the reduction of common oxidizing agents such as MnO4 and Cr2O7 2-. You should be able to understand how to combine these half equations and use them in chemical calculations. And finally, you should be able to explain how to carry out a redox titration, including how to determine the endpoint. Now at GCSE and AS level, we've seen that titrations can be used not only to add the exact amount of acid or alkali needed for neutralization reactions, but also to calculate the concentration of solutions. Now in this topic, we'll be using oxidizing agents and reducing agents instead of acids and alkalis. Now before we introduce the idea of a redox titration, it's important to recap the main principles for carrying out titration calculations. And to tackle any titration calculation, you'll need to know how to find out the following. So the first thing you need to find out is how to find the concentration of a solution. And to do this, you'll need to use the following equation. Now the concentration, which is measured in moles per decimeter cubed, is equal to the mass over the molar mass times 1,000 over volume. Now volume is worked out in centimeters cubed, mass is worked out in grams. Now this equation can also be expressed as concentration is equal to moles times 1,000 over volume. Now in addition to being able to work out the concentration of a solution, you should also be able to convert the concentration into the number of moles it contains. And to do this, we simply use this equation. Moles is equal to the concentration in moles per decimeter cubed over 1,000 times volume. So before we introduce the principles behind redox titrations, we're going to first test your understanding of how to carry out a titration calculation. And to do this, we have two questions we want you to have a go at. So here's the first question, and it comes in four parts, parts A, B, C, and D. Now parts A and B are on this slide. So you'll need a calculator for this question. So read through the question, pause the video, have a go at parts A and B, and then we'll look at parts C and D. So here's parts C and D to the first question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. Now this first practice question involves a titration between hydrochloric acid and potassium hydroxide. And in the titration we have KOH in a conical flask, and there's a 20 centimeter cube sample of this. And the hydrochloric acid placed in the burette contains 36.51 grams per decimeter cubed of hydrochloric acid. So the first question is asking you to write the chemical equation. So it's KOH plus HCl forms KCl plus H2O. Now part B is asking you to calculate the concentration of the hydrochloric acid in moles per decimeter cubed. Now we know that the mass concentration is 36.51 grams per decimeter cubed. And all we have to do here is convert grams to moles. So to convert grams to moles, you divide by the molar mass, which is the MR value of hydrochloric acid. So to work out the MR of hydrochloric acid, we need the relative atomic mass of chlorine and the relative atomic mass of hydrogen. So the relative atomic mass of chlorine is 35.5 and the relative atomic mass of hydrogen is 1.01. So that gives us an MR value of 36.51 and a molar mass of 36.51. So if we divide 36.51 grams per decimeter cubed by the MR of 36.51, we get a concentration of 1 mole per decimeter cubed, and that is the concentration of hydrochloric acid in our titration. Now part C states that 25 centimeters cubed of hydrochloric acid is required to neutralize the potassium hydroxide solution. And the question asks you to calculate the number of moles of hydrochloric acid reacting. So I'm just going to rewrite the equation for this reaction to remind me that there's a 1-to-1 ratio of potassium hydroxide to hydrochloric acid. And that means that the moles of hydrochloric acid will be equal to the moles of KOH. So to work out the moles of hydrochloric acid reacting, I use the following equation: concentration over 1,000 times volume. Now the concentration is 1 mole per decimeter cubed because we worked that out in part B. We divide by 1,000 and then we times it by the volume, and the volume is 25 centimeters cubed. So that means that the number of moles of hydrochloric acid reacting is 0.025 moles. Now for part D, you're asked to calculate the concentration of potassium hydroxide in solution in moles per decimeter cubed. So the equation tells us that the moles of hydrochloric acid is equal to the moles of KOH. So therefore, I now know that there's 0.025 moles of KOH present in my flask. And if I know the moles of KOH, and I know the volume of KOH, I can use this to calculate the concentration. So the moles of KOH is 0.025, and concentration is equal to moles times 1,000 over volume. Now the volume of KOH in my conical flask is 20 centimeters cubed. So to work out the concentration, I just do 0.025 times 1,000 over 20. Okay, and when I do that and put those numbers into my calculator, I come out with a concentration of 1.25. And the concentration is measured in moles per decimeter cubed. So it's 1.25 moles per decimeter cubed. And I can just simply write a capital M, which is a symbol for moles per decimeter cubed. So here's our second practice question, and this once again comes in 4 parts, parts A, B, C and D. Parts A and B are on this slide, and parts C and D are on the next slide. So once again, read for the question, pause the video, have a go at parts A and B, and then we'll look at parts C and D, and then we'll go for the answers to all 4 parts. So here's parts C and D. Once again, read for the question, pause the video, have a go at them, and then we'll go for the answers. So this question says hydrochloric acid at a concentration of 2 moles per decimeter cubed is added at 25 centimeters cubed of sodium hydroxide at the same concentration during a titration. And part A is asking you to write down the chemical equation for the reaction. So this will simply be NaOH plus HCl forms NaCl and H2O. And like any equation in a titration calculation, this is important because it tells you the ratio of moles of acid and alkali. So part B is asking you how many moles of sodium hydroxide are present in the flask. Well, to work out moles, we use the following equation. It's concentration over 1,000 times volume. Now the concentration of sodium hydroxide here is 2 moles per decimeter cubed because the acid and alkali are in the same concentration. So it would be 2 over 1,000 times volume, and the volume is 25 centimeters cubed. So therefore we have 0.05 moles of sodium hydroxide present in the flask. Now for part C, we're asked how many moles of HCl are therefore required to neutralize the sodium hydroxide. So once again, I'm going to write down the equation here to remind myself that the hydrochloric acid and the sodium hydroxide are in a 1-to-1 ratio. Now for part B, we found that there was 0.05 moles of sodium hydroxide in the conical flask, and as it's a 1-to-1 ratio and the moles of sodium hydroxide is equal to the moles of hydrochloric acid, we can conclude that 0.05 moles of hydrochloric acid are needed to neutralize the sodium hydroxide. Now, in all titration calculations, the equation is crucial here. It's the equation that tells us it's a 1-to-1 ratio between hydrochloric acid and sodium hydroxide, and therefore that's why we can conclude that the moles of hydrochloric acid are the same as the moles of sodium hydroxide. Now, for part D, you're asked to work out the volume of solution required to neutralize the alkali. So, for this, we know that the moles of hydrochloric acid is 0.05. So I'm going to write down the concentration equation first. Now, concentration is equal to moles times 1,000 over volume. And then I'm just going to rearrange this to work out the volume. So volume is equal to moles times 1,000 over concentration. Now, I know the moles is 0.05. And the question tells me that the concentration is 2 moles per decimeter cubed. So all I do is put 0.05 times 1,000 over 2, and that gives me a volume of 25 centimeters cubed. Now, it should be no surprise to you that the volume is 25 centimeters cubed, because the concentration of hydrochloric acid and sodium hydroxide were the same, and because of this, and is a 1-to-1 ratio, the volume of hydrochloric acid needed to neutralize 25 centimeters cubed of sodium hydroxide would also be 25. So now that we've recapped how to carry out a titration calculation, we're now going to turn our attention to redox titrations. And a redox titration is one which involves both reduction and oxidation reactions, and 3 common redox techniques involve the manganate 7 ion, MnO4 1-, the dichromate 6 ion, Cr2O7 2-, and the thiosulfate ion, S2O3 2-. Now, in organic chemistry, we've come across potassium manganate 7, sometimes referred to as potassium permanganate, and sodium and potassium dichromate solution as oxidizing agents. Now, these oxidizing agents work in acidic conditions, and we've seen them being used in the oxidation of primary and secondary alcohols. Now, an oxidizing agent is a substance that causes another substance to lose electrons or gain oxygen. And good oxidizing agents are easily reduced. Now, thiosulfate, S2O3 2-, is a reducing agent. It's a substance that causes another substance to gain electrons. Now, redox titrations can be used to determine the purity of substances. For example, they're regularly used to analyze metals and their compounds. Now we're going to turn our attention to titrations using acidified potassium manganate 7 solutions, sometimes referred to as acidified potassium permanganate. Now, acidified potassium manganate 7 solution, KMnO4, is an oxidizing agent, and it can therefore be used in redox titrations to determine the concentration of a reducing agent in solution. Now, the manganate 7 ion has an intense purple colour in concentrated solutions, and even in dilute solutions, a solution of the manganate 7 ion appears to have a strong pink colour. Now, when acidified potassium manganate 7 oxidizes a substance, it is itself reduced to Mn2+, which is colourless. So you can see here that we have MnO4 1-, where the manganese is in the +7 oxidation state, and when it oxidizes another substance, it changes to the +2 oxidation state, and +7 changing to +2 is reduction, which is a gain of electrons. Now, some teachers recommend you learn the half equation for manganate ions being reduced to Mn2+, but I feel you have so much to learn, it's much better to be able to work them out. So MnO4 1- will go to Mn2+ when it's reduced, and you have to remember that the other product is water, H2O. Now when the manganate ion is reduced, it gains H plus and it gains electrons. So I'm going to write these in now. Now because it's 4 oxygens for the manganate 7 ion, I need 4 H2O to make sure that the equation is balanced. And if I put 4 H2O there, I have 8 H's, so I need 8 H plus. So now all I need to do is make sure that the charges are balanced on either side of the equation. So we have MnO4 1 minus, we have 8 H pluses, so that's a total of 7 pluses. And on the right hand side it's 2 plus. So I need 5 electrons because 7 plus minus the 5 electrons will give a total charge of 2 plus on the left, and there'll be 2 plus on the right, and the equation will be balanced. So that is the half equation for potassium manganate 7 whenever it oxidizes something, because remember, when it oxidizes something, it is itself reduced. Now it's important that you can write these half equations, or to give them their proper title, these ion electron half equations, for the substances that are being both oxidized and reduced in a redox titration. Because when we combine these, we have the overall equation for the reaction taking place. So now let's give you some practice at writing these ion electron half equations. So here's a practice question. So it says in acid solution the bromate 5 ion BrO3 1 minus can be reduced to bromine. And I've written BrO3 1 minus goes to Br2. Now all we want you to do here is write the ion electron half equation for this process. So pause the video, have a go at it, and then we'll go for the answer. So let's go for the answer. So we have BrO3 1 minus. So I'm going to write this here, BrO3 1 minus. And that goes to Br2. And remember, the other product will be H2O, just like it was for the manganate 7 ion when that was reduced. And during a reduction, we're going to gain H plus and we're going to gain electrons. So I'm going to put these in now. And all I have to do is balance the equation. So I've got 2 bromines on the right, so I need to put a 2 in front of the BrO3 1 minus. And because I've got 3 oxygens times 2, so I've got 6 oxygens, I need to put a 6 in front of the H2O. And if I've got 6 H2Os, I need 12 H pluses so that the hydrogens are balanced. And then I just work out the overall charges on either side to balance them. So on the left hand side I had 2 BrO3 1 minus and I had 12 H plus, so that gave me a total positive charge of 10 plus. And it's neutral on the right hand side, so therefore to balance the charges so that I have the same charge on either side of the equation, I need 10 electrons. So that would be the half equation for the bromate 5 ion being reduced to bromine. So here's our second practice question. So this time we want you to write the ion electron half equation, which shows the dichromate ion Cr2O72- being reduced to Cr3 plus ions. So read for the question, pause the video, have a go at it, and then we'll go for the answer. Now for question 2, you have to write the ion electron half equation for the reduction of the dichromate ion Cr2O72-. Now when that acts as an oxidizing agent, it's reduced to Cr3+, and in all of these we have water as the other product. So I'm going to write down the H2O here. Now when the dichromate ion oxidizes a substance, it is itself reduced, so it's going to gain H plus and it's going to gain electrons. And all we have to do now is balance the equation. So I've got 2 chromiums and 7 oxygens. So I'm going to put a 7 in front of the H2O so that there's 7 oxygens on either side. and I'm going to put a 2 in front of the Cr3+. Now to get the hydrogens to balance, I put 14 in front of the H+. So that gives me a total charge on the left hand side of 2- plus 14 H+, so that's 12+. And on the right hand side we have 6+, so I need 6 electrons to have the charges balanced on either side of the equation. So this is my overall equation for the reduction of the dichromate ion when it acts as an oxidizing agent. So as I mentioned, we have half equations to represent both the oxidation and reduction processes. So during a redox titration, we have oxidation and reduction taking place. So we need to combine these equations, these half equations, to come up with an overall equation to represent both the oxidation and reduction that has taken place during the titration. So we're now going to look at how we combine these equations together. Now when combining these, you must have the same number of electrons in each half equation to enable the electrons to simply cancel out when you add them together. So we're going to first write here the half equation for manganate 7 when it oxidizes a substance. So remember, when it oxidizes a substance, it is itself reduced. So I'm going to write MnO4 1-. I'm going to have H+ and electrons, and it's going to go to Mn2+ and H2O. And to balance it, I need 4 H2O because I've got 4 oxygens on the left. This means I need 8 H+, and I then need 5 electrons so that the charges are balanced, because I have 1- and 8+, which is 7+. I need 5 electrons so that the charge on the left and the right is 2+. So now imagine that the manganate 7 ion has oxidized Fe2+ to Fe3+. I would be able to write a half equation for the oxidation that has taken place. So Fe2+ would go to Fe3+ plus an electron. So to combine these equations, I need to get the electrons the same in both equations. So I times the bottom equation by 5 so that I have 5 electrons. And then if I add these two equations together, the electrons cancel out. So the overall equation would be MnO4 1- plus 8H plus 5 Fe2+ goes to form Mn2+ plus 4 H2O plus 5 Fe3+. Now the electrons simply cancel out here because I've got 5 electrons on the left hand side of the first equation, and I've got 5 electrons on the right hand side of the second equation. So when I add these together, the electrons just simply cancel out. Now this is because if I move the electrons in the second equation over to the left hand side, there'd be -5 electrons. So it would be 5 electrons minus 5 electrons would be no electrons. That's why they cancel out. So now let's test your understanding of this with a practice question. So acidified potassium dichromate is also an oxidizing agent, and it's used to find the concentration of a reducing agent in solution. And during the titration, the dichromate ion is reduced according to the following equation. So we want you to write an overall equation to describe the reaction of acidified potassium dichromate with Fe2+ ions. So read through the question, pause the video, have a go at it, and then we'll go for the answer. So to write the overall equation, I need to first write the equation for Fe2+ ions being oxidized to Fe3+ ions. So it would be Fe2+ goes to Fe3+ plus an electron. And now to combine the two equations, I need to get the same number of electrons in both equations. So to do this, I times the bottom equation by 6. So it would be 6 Fe2+ goes to 6 Fe3+ and 6 electrons. Now all I need to do now to combine the equations is to add them together, and the electrons will cancel out. So it would be Cr2O7 2- plus 14H plus 6 Fe2 plus goes to form 2 Cr3 plus 7 H2O plus 6 Fe3 plus. Now, this equation, like all overall equations, is important because it tells us the ratio of dichromate ions to Fe2 plus ions when they react. So I can see there's a 1:6 ratio here. So in calculations, I will very often work out the moles of dichromate from titration values, and then I can use this to work out the moles of Fe2 plus present, because from the equation I can see it's a 1:6 ratio, so all I'd have to do is times it by 6. So this is why the overall equation is important. It tells me the ratio of dichromate, in this case, to Fe2 plus. So now we're going to look at a redox titration in action. So with potassium permanganate solution, we have an oxidizing agent here, and it can be used to oxidize substances such as Fe2 plus. And we can find the concentration of Fe2 plus ions in solution by carrying out this titration. And the reaction would be carried out in the presence of dilute sulfuric acid. And a known volume of solution containing the Fe2 plus ions would be measured into a conical flask using a pipette, and usually an equal volume of dilute sulfuric acid would be added. And this doesn't have to be added using a pipette, you can use a measuring cylinder for this. Now, the potassium manganate 7 solution is added to the Fe2 plus acid solution using a burette, and at first it turns colourless as it reacts. Now this is because the manganate ion is purple, and when it reacts with the Fe2 plus, the Fe2 plus immediately turns it colourless because it changes it to Mn2 plus. Now when all the Fe2 plus ions have reacted and there's no Fe2 plus ions left in the conical flask, there is nothing to turn the MnO4 minus ion colourless. So therefore, the next drop that you add from the burette will turn the solution in the flask permanent pink in colour, because you will have an excess of the oxidizing agent. Now we often refer to this reaction as being self-indicating because no additional indicator is needed here. Now this video, courtesy of the CEEA YouTube channel, shows a potassium permanganate Fe2 plus titration taking place. So here you can see we're adding the sulfuric acid to a sample of the Fe2 plus, and we're mixing it. And when we add the potassium permanganate from the burette, you can see as soon as the potassium permanganate touches the Fe2 plus solution, it turns colourless. And this is because the Fe2 plus ions are converting it to Mn2 plus. Now at the end point, we have no Fe2 plus ions present, and we see a permanent pale pink colour. So in summary, you have to remember that the manganate 7 ion is purple, and when it's reacted with Fe2 plus ions, the Fe2 plus ions convert it to colourless Mn2 plus. When there's no Fe2 plus ions present, this conversion will stop, and therefore the next drop that you add will turn your solution a permanent pale pink colour. So now let's test your understanding of what we've learnt with some practice questions. Now this question is in a number of parts, and the first parts are shown on this slide. So read through the question, have a go at them, and then we'll look at the next few parts of this question. So here's the next parts of this question. So once again, read through the question, pause the video, have a go at it, and then we'll go through the answers to all of this question. So this question is first asking you to write down the electron configuration for the manganese 2+ ion. So manganese is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Now, when it forms the Mn2+ ion, it loses the two 4s electrons, so the electron arrangement will end in 3d5. So I'm just going to put in these electrons in now. So it's 3s2. I'm then going to put in the 3p electrons. I've put them singly and then pair them up. And then there's going to be 5 electrons in the 3d orbital, and they'll fill these 5 orbitals singly. And if you had that electron configuration correct, you get 1 mark. And then the second part is asking you how you would find the endpoint or recognize the endpoint in this titration. So if you said it's the first permanent pink color, that would get you 1 mark. So for part 2 here, you're asked to state the change in oxidation state of manganese in the above redox reaction. So first of all, I'm going to write down the overall equation here, and I've obtained this by combining the half equations or the ion electron half equations together. So the overall equation would be MnO4 1- plus 5 Fe2 plus 8H plus forms Mn2 plus 4H2O plus 5 Fe3 plus. And the oxidation state here of manganese is +7 when it's MnO4 1- and +2 when it's Mn2 plus. So the oxidation state has changed from +7 to +2. If you said that, you get 1 mark. Now to calculate the concentration of the potassium manganate 7 solution, I have to use the equation and the information I was given in the first part of the question. So the MnO4 1- ion reacts with Fe2+ ions in a 1:5 ratio. And we have 20.5 centimeters cubed of MnO4 1-. We have 25 centimeters cubed of Fe2+, and a concentration of 0.0615 moles per decimeter cubed. So to work out the concentration of potassium manganate 7, I first find the moles of Fe2+, and I know this because I always find the moles of the substance I have 2 bits of information for. So I know the concentration of the volume of this. So to work out the moles of Fe2+, I do concentration over 1,000 times volume, so it'll be 0.0615 over 1,000 times 25, and that would give me 1.5375 times 10 to the -3 moles of Fe2+. Now, to work out the moles of MnO4 1-, and remember I need this to work out the concentration of the MnO4 1-, or the potassium manganate 7 solution, I need to use my equation to find the ratio. So as it's a 1:5 ratio between MnO4 1- and Fe2+, I divide the moles of Fe2+ by 5 to work out the moles of MnO4 1-. So when I do this, I get 3.075 times 10 to the -4 for the moles of MnO4 1-. And to work out the concentration, I do moles times 1,000 over volume. So that would be 3.075 times 10 to the -4 times 1,000 over the volume of MnO4 1-, and that's 20.5. So if I put these into the calculator, I will get a concentration of 0.015 moles per decimeter cubed. And remember, I can just put a capital M to represent moles per decimeter cubed. So that concludes this video lesson. So after watching this video, you should now be able to write ion electron half equations for the reduction of common oxidizing agents such as MnO4 1- and Cr2O7 2-. You should be able to understand how to combine these half equations and use them in chemical calculations. Finally, you should be able to explain how to carry out a redox titration, including how to determine the endpoint. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @Radachemistry.